Today we're going to be taking a look at 7.5, solving exponential and logarithmic equations and inequalities. The nice thing about this section is there's not anything new that we need to learn. We just have to take what we talked about in the last couple sections about being able to rewrite exponential logarithmic equations and the different properties of logs and apply them to being able to solve equations. The first thing that we're going to take a look at is how do we actually solve exponential equations. We really have three options. Option number one is the easiest, but it doesn't always work. It's write both sides of your exponential equation so that your bases are the same. If you see the same base, like 3 to some power equals 3 to the fourth power, when the bases are the same, that means that the exponents need to be the same to actually make these two sides equal to each other in the equation. This is the easiest method, but again, it doesn't always work because we can't always rewrite these two bases to be the same number. When that doesn't work, we're going to use logarithms, and we're going to either rewrite the exponential into logarithmic form, or we're going to take a look at this third option of being able to take the log of both sides. So this first problem, 8 to the x equals 2 to the x plus 6. First thing that we want to take a look at is, can we write the bases to be the same? The two bases that we see are 8 and 2. Can we rewrite one of these to look like the other one? The 8 being the bigger number is probably the one that we want to take a look at, which we can rewrite 8 to be 2 to the third power, so we're just going to change this 8 to be 2 to the third. The 8 was being raised to the x power, so the 8, which is now 2 to the third, needs to be raised to the x power. The other side we can just keep as 2 raised to the x plus 6. Here we have an exponent raised to another exponent. How do we combine an exponent raised to another exponent? Is we just multiply those two together, so it becomes 2 raised to the 3x equals 2 raised to the x plus 6. Now that we have the bases to be the same, well, if these two sides are really equal to each other, that means that the exponents, they also need to be the same thing. So 3x needs to be the exact same thing as x plus 6. In other words, 3x has to be the exact same thing as x plus 6. And now it just becomes a basic equation to solve. Get rid of the x's on both sides. So it becomes 2x equals 6. Divide both sides then by 2. And we get x equals 3. If we take a look at example B, we want to talk about trying to get the bases to be the same. Well, the two bases that we see are 5 and 200. There's not really a way that we can rewrite the 200 to be a power of 5 or rewrite both of them into a base that could be the same. So we can't do option number 1 here. So we're going to take a look at 2 and 3. Option number 2 is rewrite this into logarithmic form. So we're going to take it out of exponential and we're going to rewrite it in logarithmic form. Remember, our formula is log base b. What is our base? Of a, 200 equals x, which is the exponent, which is x minus 2. So log base 5 of 200 equals x minus 2. We need to solve this or simplify this log base 5 of 200. Again, since it couldn't be rewritten as something nice up here, it's not going to be able to be written something nice down here. So our only option that we have to solve this one is to use change of base. That property says the base of the logarithm is going to go into the basement of the fraction. So it becomes log of 200 over the log of 5, and that just equals x minus 2. This now is something that we can actually type into our calculators. Make sure that when we type it in, we close the parentheses after that 200, we close parentheses after the 5. Log of 200 divided by the log of 5 is approximately 3.29. That equals x minus 2. Add 2 to both sides, and we get x equals 5.29 as our answer. So there's option number 2. Option number 3, which is a new option to us, is instead of going through and rewriting this into logarithmic form, we can go through and just take the log of both sides. It's kind of like subtracting x from both sides, dividing both sides by 2, is we can just take both sides and write the log in front of it. This is taking the log of both sides. So log of 5 raised to the x minus 2 equals the log of 200. And if you notice, we don't have to worry about the base here. We're just going to say it's base 10. Well, to simplify this one out, since we are trying to get this x out of the exponent, we see now that it's 5 raised to the x minus 2 inside this logarithm. So we could take that x minus 2, use that property where we see a power inside a log, and move that power out in front. So it becomes x minus 2, the quantity, multiplied by the log of 5, equals the log of 200. And now it's just a matter of saying, what can we do here to get the x easily by itself? How about we get rid of what's being multiplied by it, and we divide both sides by the log of 5. Well, this now takes us to just an x minus 2 on this side equals the log of 200 divided by the log of 5, which we can then type into our calculators. Remember, keep those parentheses on the end of it when we type it in, and then we just have to add 2. But if you take a look, this thing that we get here is the exact same thing that we got over here. So it's two different methods to be able to use that is going to get us to, at some point in time, the same step, and then it's just a matter of being able to solve that. Option number 2, we just have to remember how to change things into a logarithmic equation from the exponential, and then we have to remember the change of base properties. So there's 2 real properties that we need to remember. Option 3, we just take the log of both sides, and there's only one property that we really need to remember, which is taking the exponent and moving it out in front. This option, in my opinion, is a little bit easier to do, but we have both these options that are going to take us to the same exact thing, and then it's just a matter of being able to solve it. So let's take a look at a word problem. You could choose a prize of either a $20,000 car or 1 penny on the first day, double that to 2 cents on the second day, and then keep doubling that so on for a month. On what day would you receive more than the value of the car? So first thing we'd want to do is we'd want to write out an equation. Well, the key phrase that's telling us is that we are doubling this each day. Well, if we keep doubling it, that's the thing that's going to be a growth factor, and since we have a growth factor, we are going to have an exponential equation. And since doubling is our growth factor, the number that we're going to use to represent doubling is 2 raised to the x. We just have to know what is that initial amount, what is that a value. Well, it tells us we can start with 1 penny on the first day, so we're going to start with 1 cent on the second day, or on the first day. And this needs to come out to be greater than, or when will it come out to be greater than 20,000? When will it be greater than 20,000? Well, we can ignore the inequality sign for the time being and just think about this as being something that's equal to that. How would we want to solve this? Well, one thing that we could do to try to simplify this down to make this a little bit easier for us is we see this 0.01 out in front of our exponential part. We could just get rid of that 0.01. Simplify the exponential as much as we can. When we divide both sides by 0.01, that's going to take the 20,000 to 2 million. And that's still going to be less than the 2 to the x. And now it's just a matter of being able to solve this. Well, when we go through and we talk about being able to solve it, we have this exponential again. We can't really take this base and rewrite this base to be something that looks like a 2. So the only option that we have since we're stuck here is we can go through and use the logarithms. Can't get the bases to be the same, so we go one of those other 2 options. Let's just take the log of both sides. That method might be a little bit easier. So it's the log of 2 million less than the log of 2 raised to the x. We have that again, the log of something with an exponent, so we could take that exponent, move it out in front, becomes x times the log of 2, and still have log of 2 million on the other side. Now we just have to get the x by itself. Well, the x right now is being multiplied by the log of 2, so we could just divide it by the log of 2. And the log of 2 million divided by the log of 2 is approximately 20.93. And that's going to be less than x, as in it's going to take x basically 21 days to double that 1 cent to end up being worth more than $20,000. All right, that was half of it, going through and talking about how do we actually solve the exponential equations. The other half that we're going to take a look at is how do we solve logarithmic equations. Well, logarithmic equation, again, just like the exponential, is it contains a variable inside that log. To be able to solve a logarithmic equation, we're going to do 2 things. The first one is use the properties of logs to try to simplify this down as much as we can. And then once we go through and exhaust the possibilities of using the properties of logs, we're going to go through and switch that equation into an exponential equation. So this first one, we see this log base 3 of x minus 5 equals 2. Right now it's just a single logarithm. We think about those properties that we have for logs. There's nothing that we can really do to simplify this down. So right now we can just take this, since there's nothing to simplify down, and change this into an exponential. So 3 raised to the second power is going to equal x minus 5. What's 3 to the second power? That's 9. Equals x minus 5, add 5 to both sides, and we get 14. Now, when we get an answer from a logarithmic equation, when we go through and we change it into an exponential and we solve this, we always want to check to make sure that that number still works in the logarithmic equation. So we're going to take this, plug it back in, and just say, will this come out to actually make sense? Namely, are we actually going to be able to take the log of the number that we see? So this is really just the log base 3 of 9 equals 2. We can take the log of 9, and log base 3 of 9 does give us 2, so that's going to work out. We take a look at this one. We have log of 45x minus the log of 3 equals 1. We want to try to simplify this down as much as we can in terms of logarithms. Well, the first thing we see is that we have two logs. In the last section, we talked about being able to combine two logs into a single logarithm if they had the same base. Well, we see that they both have the unwritten base of 10, and we are subtracting the two logs. When you subtract two logs that have the same base, how do we put those numbers together, as in the numbers inside the logarithms? We use division. So this is going to become a single logarithm, now base 10, where we're going to take those two numbers and divide those two numbers. So 45x divided by 3, first number, second number, and that's going to equal 1. 45x divided by 3 is really just 15x. And now it's just log base 10 of 15x equals 1. Well, now that we have this single logarithm here, we can't really go through simplify it out anymore, so let's take it and change it to exponential. 10 raised to the first equals 15x. 10 to the first is just 10. Divide both sides by 15, and 10 divided by 15 is 2/3. And again, we take that, plug that back in just to make sure that it does work, that we get numbers for these logs that do make sense. 45 times 2/3 is 30 minus the log of 3. Both of these logs make sense, so 2/3 should be our answer. D. We take a look at D. Log of x plus log of x plus 9 equals 1. Same thing going on. We have the same base of two separate logs, but this time we are adding the two logs together. Well, when we see that plus sign between the two logs, we can combine those two logs into a single logarithm. What operation are we going to use to combine the x and the x plus 9? That's multiplication. So it's going to become x multiplied with the quantity x plus 9, and that equals 1. X times x plus 9 is going to be x squared plus 9x equals 1. Now, we just have a single logarithm again. Even though we see an exponent, since we have these two things here, we can't really go through and simplify that anymore. We don't see multiplication here, so we can't break it back up, and this whole thing isn't being raised to a power, so we can't move it out in front. So this is as simplified as we get. Just the log of a single quantity equals a single number. It's as simplified as we can get in terms of logarithms. So now it's just change it to exponential. We have base 10. So 10 raised to the first equals what we're taking the log of, x squared plus 9. 10 to the first is just 10. So it's 10 equals x squared plus 9x. We have a quadratic now because we see that squared. Remember, when we have a quadratic, we want to get everything over to the same side. So subtract 10 from both sides and we get 0 equals x squared plus 9x minus 10. To solve a quadratic equation, we have options. Quadratic formula, if it doesn't work out nicely for the other options, or we could go through and we could talk about being able to factor this. So let's see if this one can be factored fairly easily. We'll create our two sets of parentheses. The last sign that we see here is minus. So that means that our two signs inside our parentheses need to be opposites, x plus, x minus. And it's two numbers that multiply to give us 10 that are going to add to get us the 9. The two numbers that multiply to give us 10 could be 10 and 1 or 5 and 2, but to add to get us the 9 with opposite signs would be 10 and 1. Since we're trying to get a positive 9, that means the bigger number, the 10, is going to need to be positive, smaller number is going to be negative. Set both of these equations equal to 0, x plus 10 equals 0, x minus 1 equals 0, and we would get 1 and negative 10 as our answers. But when we go back and we plug these two numbers in, as in log of negative 10 plus the log of negative 10 plus 9, that first answer that we get, the log of negative 10, remember our log graph looks like this. There's no such thing as having a negative x value for a log, so we can't do log of negative 10, which means this number here doesn't really exist. So negative 10 cannot be a solution. If we take a look and we'd use that with the 1s then, and replace the negative 10 with a 1, both of these numbers do work, as in they come out to be nice logarithms. So we only really have one answer, which would be x equals 1. All right, these last two problems, I want you guys to attempt for homework tonight.